introduction. Today we have Darren. He's affiliated with MIT, and he's a postdoc there, and he moved there from Australia. So that's it. Darren.
Thank you very much. So, in addition to what I put down in my abstract, in the context of being a new postdoc here that probably very few people know very much about, I thought that I would sort of split this into two halves and talk a little bit about the past, so some things that I researched for my PhD and before that, which is the second part here, a few memories of unstructured mesh methods. And then following that, I'll transition onto the layered ocean model that we've been having to think about. Okay, so just a little bit about my background. Probably opposed to a number of other people here, I don't come from a climate science background. I come more from an engineering and mathematics background. So my understanding of CFD, of fluid dynamics, was built more on industrial type problems rather than geophysical problems. So I've been here for a few months now, and I'm trying to make the bridge across from industrial applications to geophysical ones. And I just thought I'd run through a couple of things that strike me as being sort of the key differentiators between the two regimes. So one of the big ones is that obviously in geophysical problems, we typically always make some sort of hydrostatic assumption, where we assume that what's going on in the vertical velocity direction is very small compared to the horizontal. So that's totally at odds with what goes on in industrial problems, where the scale of the problem is typically comparable in all different directions, and then the velocity field is fully coupled between the three axis directions as well. So the implications that has is that you can't make any kind of simplifying assumptions to separate the pressure and the velocity fields. You have to solve it as a fully coupled problem. So in terms of computational fluid dynamics, that means that you're solving a very much more complicated and costly equation for the pressure at every time step. Another thing that I've noted is that subgrid modeling is significantly more frequent in the geophysical community, obviously because of the amount of resolution that we have to play with. So with industrial problems, even though of course you still use some sort of parameterization for some of the turbulent effects, there's a lot more direct numerical simulation that is done. So typically with industrial problems, you try to resolve all of the boundary layer flows directly by just having enough mesh resolution in those boundary layer regions. And generally, there's just a lot less subgrid problem.
Can you just, what's an industrial example of an industrial problem that you're talking about?
Okay, so it would be like this kind of thing. So my background is from aerodynamics, essentially. But you could also think about sort of mechanical engineering type problems, or even some really localized sort of S-stream type modeling. Okay, so the last one there that I've noted is that the geometric constraints are treated with, shall I say, much more fidelity in industrial problems. Typically you would use unstructured meshes to try and resolve your flow when working with industrial problems, so that you can adhere exactly to the geometry of the problem. And so again, you can use some kind of spatial adaptivity in your solver so that you can resolve all of the narrow boundary layer regions. Okay, so just as an example of what I'm talking about, this is sort of the ubiquitous aerodynamics example, solving for the flow over an airfoil section. So what you would do in an industrial problem is you need to impose all of the no-slip boundary conditions. So even though the boundary layers are incredibly thin at the top and the bottom surfaces of the airfoil, you need to locally increase the resolution of the mesh there so that you can accurately resolve that boundary layer. need to use enough resolution in the regions where interesting things are going on, so in the wake region, for instance, so that you can resolve enough of the spectrum of the eddy field, essentially. So unless you have massively powerful supercomputers, you still would use some sort of lower level turbulence closure, but typically there's an effort to capture a lot more of the eddy spectrum. Okay, now the way that those kinds of problems are tackled is by moving from, or one approach to solving these types of problems is to move away from structured meshes. So rather than having meshes made up out of uniform quadrilaterals, we go to some sort of triangle-based data structure. So there are lots of different flavors of different unstructured meshing techniques, but the one that I've had something to do with in the past, and the one that I'd argue has a lot of mathematical elegance about it, is something called a Voronoi-based scheme. So a Voronoi diagram is a set of polygonal regions. So in this case, on the diagram there, it's the hexagons. And these polygons are special in some sense. So the thing about them that is interesting is that they satisfy what's called an orthogonality constraint. So what that means is that the center of the Voronoi regions, so that's the little red vertices, are orthogonal or perpendicular to all of the edges of the Voronoi set. What that allows you to do is construct highly accurate numerical schemes, which essentially are quite similar to the type of staggered grid structured schemes that we would typically use in geophysical applications. Okay. Another thing to say about these kinds of numerical methods is that definitely there's no kind of finite differencing that's applicable here. So when you move away from sort of regular quadrilateral discretizations, you have to go either to a finite volume scheme or to a finite element method. So I'll talk a little bit about finite volume methods because that's what I've worked on in the past. So in a finite difference context, typically you would try and approximate all of the derivatives in the equations of motion directly by taking the value at 2 grid points, taking the difference of that, and then dividing by the length in between. With a finite volume scheme, on the other hand, you instead are integrating what's called the weak form of the equations of motion. So that's essentially looking at the conservation laws in integral form. So rather than trying to approximate the derivatives directly, you instead turn everything into a contour integral around a set of discrete cells. So the red vertex at the center of the diagram there essentially is representative of a certain concentration of a particular quantity. And the way that concentration is evolved in time is based on the integral of the fluxes through all of the edges of the Voronoi cell. So again, this is where the orthogonality comes back into it. Because the normal flux directions are orthogonal to the different Voronoi vertices, that's what gives these type of methods a lot of accuracy. Okay, so one last thing I'll point out is that the Voronoi diagram, even though in this case it's made of hexagons, it's based on an underlying triangulation. So what that means is that for different formats of the underlying triangulation, the Voronoi cells might take a different shape. So Voronoi cells are able to maintain all of these orthogonality properties even when the mesh is non-uniform. So you can have Voronoi polygons that don't have 6 edges. You can have some that have 4, 5, 6, 7, 8 edges, and all of the orthogonality constraints are still satisfied. Okay, so what that allows you to do then is to have spatially adaptive meshes. So you can have very small Voronoi polygons in the boundary layer regions, and then you can transition out to much larger Voronoi polygons in areas where the flow is more uniform. So the Voronoi polygons look pretty regular in this mesh, but if really sort of squint at it, you can see a couple there that don't have 6 edges.
Can I ask you? So this, remember the resolution dependence can be not just in the vertical, you could have it, let's say, in the horizontal, just to, let's say, closer to a boundary.
Yeah, exactly. So when dealing with industrial problems, you would have fully 3-dimensional mesh adaptivity. Okay, so one of the things that was a big focus of my PhD was about how you can generate these kinds of unstructured meshes and how you can do it in a way that is automatic, so it can just be done by a piece of software, and so that it is somewhat optimal. So just a couple of the constraints that you want to satisfy. There are both size and shape constraints on the elements. So if you generate either triangles or Voronoi polygons that are highly skewed or distorted, then that's not going to give you a good approximation to the underlying PDEs. So definitely you want to try and aim for equilateral triangles, which corresponds to regular hexagons for the Voronoi diagram. Another thing that's important is the rate of transition between the different sizes of the elements. So if you start off with a tiny element that's located right in boundary layer, you can't automatically then transition to an element 100 times its size as one of its neighbors. Okay, so in terms of addressing the optimality of the mesh, it can become quite a difficult problem because you have to choose a set of vertex positions that are somewhat optimal, and you also have to choose an optimal mesh topology. So that essentially is how you choose to connect the vertices together into a triangulation. Okay, so one of the things that makes life a little bit easier is what's called the Lonnie triangulation. I won't go into all of the specifics with this, but essentially the takeaway point is that if you give it a set of vertices located in any dimensional Euclidean space, it will return you a topology that is somewhat optimal. So it essentially can decide how to optimally connect up all of these vertices into some kind of a triangulation. So what I mean by optimal is that typically the angles of the elements that are formed, the minimum angles are maximized, so you don't have any super skinny acute triangles. Okay, so once we have the notion of a de Lonnie triangulation available to us, we can consider different ways in which we can construct a mesh generation algorithm. So typically what you start off with is just the external geometry that defines your domain, so just the external perimeter of the flow region, and then just the geometry of the aerofoil in this case. So one way to approach the meshing problem is by doing what's called de Lonnie refinement. So that means that you construct a coarse triangulation just of the external geometry, and you then incrementally insert new vertices according to a particular strategy that's designed to improve the shape of the mesh. So again, I won't go into all of the specifics of it, but the main point here is that if you insert vertices at special points, which are the centers of triangles, points called the circle centers, then you can replace a low quality triangle that had very poor angles with a sequence of higher quality triangles. So this kind of algorithm has the mathematical guarantee that if you do insert more vertices specifically at these special points, the quality of the triangulation is always guaranteed to improve. So you essentially just continue adding vertices in these particularly special points until all of the different geometric constraints that you impose are satisfied. So typically you would say that the minimum angle between any edge in the triangulation has to satisfy some kind of criteria, and also that the size of the elements in different regions of the domain have to be less than a certain threshold. So in 2 dimensions, this type of de Lonnie refinement scheme a minimum angle greater than 30 degrees. So that means that all of the triangles are typically reasonably well shaped. Okay, so working in 2 dimensions is fine in terms of illustrating the concept, but the more interesting problems are the ones that occur in higher dimensionalities. So 3-dimensional triangulations can come in 2 kinds. So this is a mesh of a turbine blade from a jet engine, and the mesh on the left is what's called a surface triangulation. So it essentially is just the skin of the turbine, but the interior volume is empty. The mesh on the right is a cutaway version of what's called a volumetric triangulation. So that's actually built out of little tetrahedral elements rather than triangles. And dealing with the way that the refinement algorithms work in the fully 3-dimensional case can get extremely complicated. And even though it's something that needs to be used in lots of different forms of numerical analysis, the fully 3-dimensional problem is still actually unsolved theoretically. So no one has yet proposed a particular algorithm that can guarantee a lower bound in terms of the angle between the faces of tetrahedrons.
Next question. So, for like the airplane wing that you showed. So for this flow, it's very important that the material that it floats on is very smooth.
Yeah.
So if you make it a little bit rough, even rough paint or so, the flow is very different. And it seems with this, there's also always some roughness in the mesh that you put on there.
Do you mean because the edges are linear?
Yeah.
Okay.
Or can you really? So maybe you should show a zoom or so of the boundary layer. But is the boundary of the mesh really smooth on the surface?
Okay, so if you have a finite volume method, that is only linearly accurate, then it makes sense to have a mesh which is a linear approximation to the geometry.
Okay.
So if you have a second order accurate numerical scheme, then having triangles with straight edges is sufficient. If you go to a much higher order finite volume scheme, then you need to introduce some curvature to the edges of the triangle to cater to exactly what you're saying.
Yeah. Okay.
So that is something that's investigated as well. I wasn't going to go into that here, but that's definitely what happens. So typically the curvature of the edges is of the same order of accuracy as the numerical scheme. So if you have a numerical scheme which is based on quadratic functions, then the edges of your triangles would be quadratics as well.
Yeah. Okay.
Okay. So to start to come back to what's probably more familiar territory for most people, it's not inconceivable to consider an unstructured mesh GFD solver, so either for the atmosphere or for the ocean. So you would build this scheme based on exactly the same sorts of considerations that I was talking about before for the industrial problems. So in this case, you would use the surface mesh generator to generate a surface triangulation that adhered to all of your different geometric constraints. And in this case, this is just a really quick mock-up that I made. I imagine that you could refine according to steep regions of topography in the ocean floor, for instance, or particular regions where there was a very powerful energetic exchange between ocean and atmosphere. Anyway, this kind of unstructured mesh would allow you to have that kind of spatial flexibility and adaptivity. Once you've generated the unstructured triangulation, you can then generate a surface Baroni diagram that you could use to construct a staggered finite volume scheme. So one thing, so I guess with this kind of approach to GFD problems, you could sort of list some pros and cons. So definitely all of the flexibility and the spatial adaptivity is one of the huge benefits of this type of approach. Another big benefit is that there's no grid singularity issues. There's no polar singularity. There are no regions of the mesh, like corners of cube spheres or anything like that, where special care with a numerical technique is required. And it would allow you to run a different regime of GFD solutions, essentially. If you were interested, for instance, in running a high-resolution regional model that was embedded within a coarse resolution global model, then this kind of spatially adaptive mesh would facilitate that directly. Okay, so there are all of the good points. On the downside, this type of scheme, if you are primarily interested in running fairly uniform resolution, globally coupled runs, would probably be less efficient.
Why? I mean, where will it break down?
So with a uniform mesh, you essentially only need to compute all of the interpolation coefficients that you use when evaluating the fluxes just for one element, because then you can just map that element to any other element in the mesh. With an unstructured mesh, every element is special, essentially. So every element needs to be treated as a special case. So you need to compute and then store all of the interpolation coefficients for every element in the mesh.
But this can be done only once. I'm sorry. But this can be done only once, right? And then for the whole integration, you can keep the initial set of. So that doesn't seem to be a very heavy cost.
So I personally am a big fan of unstructured meshing approaches, but definitely the numerics is more complicated. There's probably a much bigger sort of learning curve, I guess you could call it, in terms of getting it set up properly. Another big downside is that the time step restrictions for the numerical scheme scales with the smallest element in the mesh. So if you have a hyper-refined mesh of the fjords in Scandinavia or something, then the global model will time step at that restriction. There are a few ways around that. You can, for instance, allow different elements to time step at different rates. So this is a technique that they use for galactic stellar integrations, for instance. But I guess at that stage, the numerical scheme is starting to become quite complicated. Anyway, I'm not necessarily advocating that we should change all of the model and that we should implement something like this at all. But I'm just pointing out, I guess, that there is some sort of crossover that we can take away from some of the techniques used in industrial applications and think about ways that we can use it for GFD. Another thing I'd say is that a couple of the big GFD groups are going down this path. So NCAR, I believe, has the MPAS model, which is based on exactly this kind of surface for any diagram. So one of the things that they've been using it for is to have regionally refined eddy resolving regions, coupled to a background coarser global mesh.
Are you only talking about the ocean now, or is this NCAR model also doing the whole model?
So I believe that NCAR uses an unstructured grid for the atmosphere as well, but it's the ocean that I know more about. So I had a quick discussion with one of the NCAR guys at some stage, and they were saying that they found it quite useful in terms of being able to locally refine around high energy exchange regions between the ocean and the atmosphere, and that was helping the accuracy of the coupled runs. But that's totally secondhand comment. I have no personal experience with that.
I mean, the problem is obviously more complicated in the ocean.
terms of dealing with things like coastlines and whatnot, as long as you can generate a mesh for the object, then essentially all of that complexity has been taken care of. So definitely based on those Lonnie type procedures that I spoke briefly about, it's fairly straightforward to incorporate all of those types of constraints.
Can you also make it adaptive, so that if like in the ocean there's an eddy somewhere, then you make it very fine there, and where there's nothing going on, it's
so that's the coolest of cool sort of numerical methods. There is a significant overhead to doing that kind of thing. So as was said before, as long as the mesh is static, you can pre-compute all of these complicated interpolation coefficients. If you start allowing the mesh to move at every time step, say, you would have to recompute everything at every time step. So people sometimes play some funny games where they take 100 time steps at a fixed mesh and then adapt the mesh, recompute everything, and that helps them offset the cost of having to do the computations. Okay, so if anyone had any more questions about the past, I guess now would be the time. But otherwise, I'm going to transition into the discussion of the vertical representation of the motion model. Okay, so at this stage, I guess I'll just mention that what's going on at the moment is that the Russell GISS ocean model is undergoing a bit of a refurbishment. So both Max and I are working on a few different ideas that we hope is going to go into the next iteration of the model. So Max has done heaps of work on the horizontal discretization, different cube-like sphere options, and I'm essentially working orthogonal to him, looking at the vertical discretization. So hopefully over the course of my postdoc, we'll be able to bring these two sides of the equation together and have a new model which has an updated horizontal and vertical treatment. Okay, so I'll just skip forward for a second, just to have a look at this diagram. So this is a slice from a HiCom run, which is showing the layer-wise stratification of temperature. And essentially, the complexity of this plot is driving some of our decisions in terms of the vertical discretization. So HiCom, as I'm sure everyone knows, was one of the pioneering codes to have a flexible vertical discretization profile. So it allowed for a pseudo-optimal representation in some regions of the ocean, in the open ocean where it made sense, and it was able to use a different vertical discretization when it needed to. So in shallow regions of the ocean, it could transition to what's more like a sigma coordinate, which follows the topography. And in the upper regions of the ocean, in the mixed layer, it's able to adopt more of a fixed height representation, where there's not very much, or where there's essentially no change in the height of the layers. So those three different regimes essentially are optimized to achieve different things. So an isopycnic representation is handy in the open ocean, where we want to enforce what's known as the adiabacity of the flow. So essentially, if you have a flow, if you have a parcel of fluid at a particular potential density, it will typically flow to another region at the same potential density. So it doesn't necessarily transition along trajectories of constant height or pressure or anything like that. It follows these isopycnic surfaces. If you construct a numerical scheme which essentially incorporates this kind of behavior as one of its key assumptions, then it can reduce the amount of spurious vertical mixing that goes on in the model. So essentially, our aim is to have a layered ocean model where the flow in isopycnic regions of the ocean only occurs locally within each layer. So that means that the amount of mass in a particular as long as this isopycnic assumption holds. The other thing that we want to do though is to incorporate a bit of flexibility. So while most regions, or while a large percentage of the ocean does obey this type of isopycnic assumption, there are regions of the ocean where it breaks down. So that's regions like the mixed layer, say, and also shallower regions where the topography becomes important. So essentially our aim is to come up with a new vertical discretization technique that's able to choose between those three regimes as it sees fit. Another thing that we're trying to do is we're trying to allow those decisions to be made dynamically. So if at a particular point in time, a particular region of the ocean is heavily stratified, so that the isopycnic assumption is good there, we want that region of the ocean to behave in an isopycnic way. But if you come back at a different time of the seasons, maybe those assumptions don't hold anymore, then you want the model to be able to transition to a different regime. Okay, so the way that we are approaching this problem is to go down the path of what's called an arbitrary Lagrangian Eulerian scheme. So what that does is it allows the model to behave in what's called a Lagrangian fashion, where the mesh moves with the flow. But then in special cases, we can allow it to revert back to more of an Eulerian framework, which is where mass transport occurs as a result of fluxes through layers. Okay, so I think I've covered most of this. Definitely our approach is inspired heavily by HiCom, but we are trying to make a couple of decisions differently to what's done in HiCom. So in terms of the equations that we're working with a set of layered equations. We're using pressure as the vertical coordinate, but we're not necessarily assuming that the layers have a constant profile in terms of pressure. So what we've got then is we've got the momentum equation for the horizontal velocity components. We've got the hydrostatic equation in terms of geopotential and pressure. We've got an evolution equation for what's called the pressure thickness, so that's the delta P variable there. And the delta P, that dictates the thickness in pressure space that the layers have at different points in space and time. So fluctuations in delta P, that essentially you can think of as layers floating up and down. Okay, and then finally we've got the thermodynamic evolution equations as well. Okay, so one of the ways that we're looking to do something slightly different from HiCom is in the way that we integrate these equations. So I don't want to talk too much for HiCom. I'm sure that Rhino would have to be here to really tell us exactly what it does. But my understanding of what HiCom does is that essentially it's a little bit more like a finite difference code, so that it allows these sloping coordinate surfaces to develop at different regions in the ocean. And then it tries to approximate the different differential terms in the equation of motion by taking finite differences along these sloping layers. What we're trying to do instead is to take a finite volume approach to the problem, which allows us to use pressure as the vertical coordinate everywhere, but to integrate over layers that have variable thickness in the pressure direction. Okay, so I talked a little bit before about the idea of having both a Lagrangian and an Eulerian treatment of the equations of motion, and I'll try and make that a bit more specific at this stage. So in a purely Lagrangian method, the grid moves at exactly the local flow velocity. So there are essentially no fluxes that occur between cells. It's just that all of the cell interfaces drift exactly with the local flow velocity. When you're trying to maintain something like an is exactly what you want to have happen, because you want the net amount of fluid in the layer at this time step to be exactly the same as the mass at a future time with the layer in a different position. One of the problems with purely Lagrangian methods is that because of this grid motion, the grid may become tangled and distorted. So it may start to violate some of the geometric constraints that you have for it. Another thing that the grid may do is it may drift away from what you have decided is an optimal configuration. So in both these circumstances, we need to incorporate the Eulerian part of the algorithm. So what happens with the arbitrary Lagrangian-Eulerian, or the AL approach, is that you take a sequence of purely Lagrangian steps, and if the grid has evolved into a configuration that violates some of your constraints, you interpolate back onto a target grid of your choosing. And that interpolation process can be thought of essentially as fluxes flowing through the layers.
So that's done in the one-dimensional. So at each grid point, you will do this process in the vertical, right?
Yeah. So this is only in the vertical chord. The horizontal grid is always totally static.
But it will be done separately, for example, or are you going to have fluxes from neighboring boxes too?
So the horizontal treatment is done in flux form, so that's always with fluxes. There's no grid motion. And in the vertical, we're trying to have it so that there should never be any explicit vertical fluxes. There's only this interpolation process.
So that's interpolation process is done only in the vertical.
Only in the vertical, yeah. Okay, so to try and give you a really quick sketch of what a time step of this type of Lagrangian-Eulerian algorithm. The first thing that we would do is we would integrate the hydrostatic equation to get the geopotential profile per column. And we can then use that geopotential profile to calculate the horizontal pressure gradient. Taking a finite volume approach, you can use that information to step forward and find the new layer-wise integrated velocity components, which you can then use to update the pressure thicknesses. And you do a similar sort of thing for the thermodynamic variables and the other traces as well. Okay, so at the t plus delta t level there, the grid will have drifted due to vertical transport. So in the evolution equations, both for the traces and for the momentum and the thermodynamic variables, there's no explicit vertical flux. It's only grid motion. So at t plus delta t, the grid has moved with the flow. And at that stage, if we decide that the layer-wise levels are not where we want them, then we do this remapping process.
You say the second equation should be another delta p equal delta p times u.
You're right. Yeah, that's a mistake.
God.
Got me, Karen. Okay, so a more visual representation of that process. So if we just consider just a single column of fluid, then where we are at green on the left is at the known time level. So we solve all of those equations of motion, step them forward in time, and we get the new cell mean values with perturbed layer interface positions. Now, if at that stage we decide that that new mesh is fine, then we don't need to do anything more. We just accept it as a purely Lagrangian step. If, on the other hand, we say that that new grid is not where we want it to be for some particular reason, then we have to do the interpolation process. So I won't go hugely into the details, but essentially the way that that works is that there's a particular set of polynomials that's reconstructed for each of the cells per column. The levels of the new mesh are selected based on whatever criteria you're working with. integrated over the thickness of the new layers to give you the updated cell mean quantities. So this kind of approach to the interpolation is important in that it's conservative, so make sure that you don't create or destroy mass. And by constructing polynomials of a high enough order, you make sure that this type of interpolation is not very diffusive.
So one thing that Max did or something, I don't know whether it's in the ocean model right now. So the curved blue line.
Yep.
So it's not matching at the edges.
It's discontinuous.
Discontinuous at the edges. And so sometimes when you're, I guess you probably will be doing this less frequently, but one thing that Max thought about the ocean model is that, you know, these edges go up and down, and the fact that there's discontinuity at the edges that, you know, causes things to not be nice. Every time you go up, you're using one value, and every time you're going down, you're using a different value. So what do you think about that? It's the fact that you're doing this movement less frequently. It doesn't matter that much, or?
So I think unfortunately it's a bit of an unsolvable problem from my point of view. So the problem is that there is this three-way tussle between mass conservation, imposing continuity at layer interfaces, and monotonicity. And I don't think it's possible to design a scheme that satisfies all three. So if you allow for discontinuities, you can get monotonicity and conservation. If you sacrifice monotonicity to get continuity, then you can get a scheme that can give you spurious oscillations. So I agree, I guess. If it were possible to construct a scheme that was continuous and monotonic and conservative, then that's what we would optimally do. But I'm not aware of a scheme like that.
Does it play a role when you do this vertical regridding versus, for example, your horizontal fluxes and so forth in the code? Is the order of operations important?
So by the time you've done the Lagrangian step, all of the fluxes are incorporated at that stage, so the horizontal fluxes are already in there. So when you do the remapping step, that essentially is just partitioning one layer, one layer into some parts that go into the top layer and some parts that go into the bottom layer. So because the horizontal transport is already in there, as long as you do that partitioning accurately enough, everything should work out.
Well, so are you planning to, so next, in the current code has this quadratic upstream scheme, you know, so in the vertical there's like, in addition to a mean, there's a lit gradient and a quadratic second order moment. Are you planning to keep that, or what are you thinking?
So I've been playing around with a few different polynomial reconstructions essentially. So what I'm using at the moment is PPM, or a sort of mutant version of PPM that I've come up with. You can go to higher order than that as well, but the tests that I've done so far, PPM has been enough. I guess as you were saying before, because this process is not done as often as a vertical advection was done, or is done in the current model, maybe the accuracy isn't quite as critical. Okay, so talking about one of the chief challenges with this kind of model, one of the big challenges is an accurate evaluation of the pressure gradient force. So essentially, because we have these sloping surfaces, so you could interpret a sort of HICOM view of the situation as being these sloping surfaces. And in the finite volume technique that I'm trying to develop, you have layers of non-uniform thickness that are also at different vertical heights. It's problematic to try and calculate an exactly horizontal pressure gradient. And one of the problems is that the vertical force balance can start to contaminate the horizontal force balance. So typically the problem manifests in regions of sharp topography, where there's also heavy stratification. So the nonlinearities in the equation of state give rise to what's commonly known as the pressure gradient force error. The reason that it's such a problem is because if the magnitude of that error is too great, you can have an ocean that should be at equilibrium start to move spuriously and spontaneously. Okay, so one of the approaches that is sort of the well-known approach to deal with this, I believe that this is the type of approach that's used in ICON, is to essentially have a two-term pressure gradient evaluation. So you have to try and evaluate a finite difference on the sloping coordinate surface in pressure and also in geopotential. That typically does work reasonably well, but as I was saying, one of the problems in regions where the topography becomes really sharp and where there's significant nonlinearity in the equation of state, you can get these issues with spurious motion. So instead of that, we're trying to stick with the finite volume framework, extending some work that was done by Adcroft and some of his colleagues at GFDL, to instead evaluate the pressure gradient term via a finite volume integral. So rather than trying to approximate the differential operator, we instead turn it into a contour integral. So the pressure gradient then is the integral around the exterior of the finite volume, where we're integrating for the geopotential. Okay, so a diagrammatic version of that would be this little quadrilateral here. So if we're trying to integrate for the x component of the pressure gradient, then we need to consider a scheme that has 4 different segments to the contour integral. So you have to integrate the geopotential on both the left and the right side, but you also have to integrate it along the slanting top and bottom surfaces of the cell. Another thing to point out is because the equation of state is nonlinear, the geopotential is nonlinear across the thickness of the element. So that means that when you're doing these integrals, if you're doing them numerically, you have to use a quadrature rule which is of sufficiently high accuracy. Okay, so this is something that I've been focusing on lately, trying to come up with an appropriate numerical technique for this this term. So the type of test case that I've got set up is just a bit of a channel with some various topography, with some really extreme topography at the left and right ends. So it's a 200-kilometer channel. It's 2,000 meters deep. I'm using a fully nonlinear equation of state, and there's linear stratification in the thermodynamic variables. Okay, so essentially, if you don't integrate the pressure gradient term accurately enough, you get to this kind of situation. So if you can see right where the topography changes steeply, there's a whole range of non-zero velocity components. And if you can see the scale down the bottom, essentially we've got flow of a few centimeters a second. So this would be an issue in terms of maintaining equilibrium. On the other hand, if you go to a very high order numerical technique for integration of the pressure gradient term, so in this case I use some 5-point quadrature rules, then you're able to evaluate the pressure gradient so that you get essentially numerical precision in terms of the error. So the scale down here is 10 to the minus 14 for the velocity components. So even though it maybe doesn't look like the most exciting of oceanographic plots, this is actually a really big deal when it comes to layered models. So being able to maintain equilibrium so one last thing that I'll go through is just a quick example of where the model is at the moment. So I've been working just on a two-dimensional model, or so it's a 2.5-dimensional model, so it's periodic in the outer plane direction. And this particular test is a dense overflow type case. So there's a chunk of dense water sitting up the top left, and it essentially is trying to flow down the slope to get back to its equilibrium state. Now, one of the things, another benefit of using a layered approach for the ocean model is that you get a more accurate representation of bottom topography. So essentially with this layered approach, we're getting a piecewise linear representation of the bottom features. So I'll just step this flow forward, and you can see that a big blob of the dense fluid makes its way smoothly down the slope, and then does essentially what you expect it to do, and it will slosh back and forward until it finally reaches its equilibrated state. So in contrast to some of the fixed height coordinate models that are in use at the moment, the piecewise linear treatment of the bottom topography is quite important for this type of downslope flow. So the effect, I think, is typically called staircasing with a fixed coordinate model, whereby the fact that the flow essentially has to try and flow down a series of steps in the bottom topography causes it to break away from the bottom before it actually gets there. So another advantage of the layered model is that hopefully we'll get a more accurate representation of these type of flows.
What do you have in this plot for surface? Do you have any changes through? It's just
no, it's just atmospheric pressure without any stresses or anything.
And vertical mixing processes?
No vertical mixing in this model. So this essentially is just a road test of the Hegel scheme. Okay, so that brings me toward the end. Where I'm at the moment is that I have this 2.5-dimensional model working well, I feel. So the pressure gradient formulation is maintaining the type of constraints that I think it needs to. And I'm able to simulate a variety of different 2D flow conditions. Where we can go from here, still within the 2D model, is we can investigate some various other numerical features. So one thing would be to be able to have variable numbers of layers per column, and then to start to flesh the model out, as you were saying, to try and have some general boundary conditions, and to try and incorporate some of the various parameterizations.
One of the problems that HICOM has, for example, is when you introduce, let's say, freshwater flux at the surface, right? And then you change even your targets are not densities, are they? Because in HICOM, for example, the target coordinate is in density space. Yep. And for example, when it rains and your first layer gets so fresh that you are running out of representation there.
Yeah, so the particular strategy to try and choose the layer targets is something that we're still working on.
But so you are going to have target densities, right? That's where
so
you're
it's all up for grabs at the moment. Definitely that's sort of the obvious thing to do, but we are trying to come up with something different. There are various things that HICOM does that maybe it shouldn't sometimes. Yep, so finally, I guess the end goal, as I was saying earlier, is that the next iteration of the GISS ocean model should hopefully incorporate this sort of technology, and that will allow us to play around with various different representations for the boat.
Questions?
So
current model is the target is the same at every location. You're thinking of changing the target based on grid cell location and stuff like that, I suppose.
We haven't made any decisions. So Max has sort of thrown down the gauntlet to see whether we can do better than that, and it's unclear to me whether it's possible or not. So I guess one thing that's handy about this kind of algorithm is that you can try it in various different configurations. I mean, the way that you specify these layer targets is sort of arbitrary, really. So if at any time in the future you could come up with some kind of fancy scheme to choose these targets, then you can just put it into the model and it should work.
Well, the problem is that, for example, when you are doing climate change scenarios, right, then you go through such a wide, range of values for all these properties that it can become a problem. Otherwise, you will have a very wide. Then you would have either to have too many layers with very thin resolution, or you will be missing coordinates where you need it at some point of the integration. And then what, for example, then the issue becomes also what happens when you are collapsing layers. Do you have, I mean, HiCom has, for example, you can run out of mass in a layer.
Yep.
Disappearing layers.
Yeah, so that's not currently implemented, but that's definitely on the to-do list.
Okay, thank you.